I think I covered this also one time before. I'll just show it one more time, and that's that. Here you see reflection. If you put yourself in front of a mirror, you can see that every inch of you, and I'm sure that if you could go to the atomic level, we could even talk about every atom in your body is mirrored, to use the term, directly in the mirror. In other words, it's straight ahead. It's back and forth. How does Mother Nature do this magic trick? Are you shooting particles at the mirror that are bouncing and coming back? I mean, remember, the Earth moves around the sun. So, they should be, all these particles should be, no matter how you look at it, should be going as a curve, right? Especially when general relativity says that gravity pulls on light, brings light down. We were able to measure that through the Harvard Tower experiment. Remember that? And so we got a little bit of problem because, according to general relativity, light only travels in curves. It can never travel in a straight line. And yet here you are in front of a mirror. You could swear that it's a straight line. And yeah, these guys will say, well, we would have to measure that, and we can't measure that, so we don't know. Okay, let's find out. Let's find out if that's even possible to have a different conclusion that, that light travels straight, or really travels rectilinearly, or extends straight. Okay, that's the correct language. Okay, here we have an example, okay? Ray reversibility. And again, if you shine a light through a prism, or a lens in this case, against the mirror, light apparently travels in the same direction, along the same path in the opposite direction. And I mean, if it's straight ahead, you would say, well, it just hit and came back. But here you have the mirror at an angle, and yet again, you can show to yourself that the mirror will reflect it back through the lens, back to, if you had a mirror there where you have the flashlight, it would reflect it right back to it. How does Mother Nature do this trick with particles? Okay, so this is the issue. And I talked about this a little while ago. The lunar ranging experiment that NASA and the Russians have done. And here's the problem that you create with light traveling in curves according to relativity. You have a retroreflector on the moon. You're going to shoot a laser at it, right? It's a little over a light second away, 2.5 light seconds round trip. And that's what's going to happen. The Earth is going to move around the sun. The moon is going to move around the Earth. So you've got a difference in the time you send it out and the time you receive it. And now you're going to have curvature of space. Remember, the Earth weighs down space-time. So those little marbles, those photon marbles, are going to roll down the curvature of space-time. So how does that curvature get to the retroreflector and back to you? You would think that the folks out there, the ones who work with this, are pointing the laser directly at the retroreflector. In fact, that's what they do. They, like I showed the other day, they have this crater, which is something they can more or less see from Earth, and they have the retroreflector somewhere in there, and they know that if they point their laser, which has a diameter of like anywhere from 4 to 6 kilometers wide, they know they're going to hit the retroreflector, and they're going to have a signal come back to them, like a little shining little thing, and it comes to their detector, and they say, okay, well, there's the reflector, and we know we hit it. It's not like they see it. It's like they shoot it, and if they get a signal back, they say, okay, we hit it. That's how it works. Okay? And what they're trying to determine is how far the moon is and whether it's flying farther out or getting closer to Earth. That's the point of the laser ranging experiment. But if you have the curvature of space or space-time, then you got a little bit of problem, because all those marbles, photon marbles, they're going to roll downwards, very steep, by the way, because the Earth is weighing down space-time in order for the moon to go around it like a little ball around the roulette. You have to have a depression, which is what they illustrate and explain, and both. So you have the Earth weighing down the canvas, right? Now the little photon balls, they have to go through that same curvature to reach the moon. Whether it's in 1 second or not, it doesn't matter. They have to go through curvature. And so you're saying it goes through curvature, hits the retroreflector, and now the Earth and the moon meanwhile moved, and now it's going to come back through that same curvature and hit the Earth, hit the detector? Yeah, sure. Again, their explanation is what's irrational. That's what I'm criticizing. Okay, so here we have Mr. Feynman. He's going to explain to us reflection. Okay, fortunately, he did a good job on that, and I hope you learned reflection from him today. Okay, all that we know, Mr. Feynman is perfect for that. He was a good teacher. Good in the sense that he could teach subject matter very nicely. He was a good person who could expose the theory. But the question is whether the theory has any rationality whatsoever. And we'll let Mr. Feynman speak for himself, for all of quantum mechanics. Okay, so the first thing he warns you about, he says, people are always asking for the latest developments in the unification of this theory with that theory, and they don't give us, the mathematical physicists, right, a chance to tell them anything about what we know pretty well. So he wants to tell them something, but that's not what people ask. What people ask is what they ask in places like Quora. How does gravity work? How does magnetism work? That's what people want to know. That's what they want to understand. That's what they want people like Feynman to explain. And that's not what they know. That's not what they can explain. And that's not what they tell them. They say, look, we don't want to talk about that. What do they want to talk about? They always want to know the things we don't know. Yeah, I like that from Feynman. Yeah, because he's not a physicist. That's why. A physicist is a guy who can explain what he cannot explain. That's a physicist. Otherwise, he's a mathematician, just a petty mathematician who does what? What does mathematics do? Descriptions. That's all math can do. Math is a descriptive language. It's not a science. It has nothing to do with science or with physics. Physics is not about math. Physics is about explaining a mechanism. That's the difference. And what these people never were able to do in the last 100 years, since quantum mechanics at least, is explain a mechanism. Okay, so this is the problem, because that's what people want to know about reflection. You look at yourself in the mirror and you ask, how does that work? How does that happen? How does Mother Nature do that magic trick? And these people say, ask me a question that I can answer. Like saying, that's not one of them, okay? Okay, so here's Mr. Feynman. He's going to tell us everything he knows about reflection. Here it is. He says, the strange theory of light and matter, QED, quantum electrodynamics. What I'd like to talk about is a part of physics that is known rather than a part that is unknown. So he says, this is known, okay? Okay, what is it that they know? I would like to tell you about a subject that has been thoroughly analyzed. He says, attempts to understand the motion of electrons going around the nucleus by using mechanical laws, analogous to the way Newton used the laws of motion to figure out how the Earth went around the sun, were a real failure. What is he talking about? Well, he's talking about this. He's saying we cannot explain how an electron goes around the nucleus and falls from one energy level or orbital to another and comes back. They cannot explain that, not with particles. And so they don't have a mechanical explanation for this. Okay, this is the issue. This is what he's saying here. He says, attempts to understand the motion of electrons going around the nucleus were a real failure. Okay, we got that? Let's keep that in mind. He's telling us they don't know. And he cannot explain what you want to know. He's going to tell you what he says they've proven and know for a fact. Okay, let's find out what it is they know. Okay, here he's continues. He says, the theory of the interaction of light and matter, quantum electrodynamics, was finally developed in 1929. But the problem here is that he goes through this and he says, first he says they proved it through experiment and it all matches, great. Okay, then he says, I would like to again impress with you with the vast range of phenomena that the theory quantum electrodynamics, what? Describes. He's not going to explain. He's going to describe. And he says it's easier to say it backwards. The theory, what? Describes all the phenomena, etc., etc., etc. He's going to talk about descriptions. He's not going to talk about explanations. And that's what we want to know. We want to know how reflection works. And he said, well, I'm not going to answer that question. I'm going to tell you a description. Okay, and what's he going to describe? Let's find out. Let's find out what Mr. Feynman, the great Feynman, is going to describe for us. Okay, I must clarify something. When I say that all phenomena of the physical world can be, what? Explained by this theory, we don't really know that. These are his words, okay? I'm not putting words in his mouth. We have found nothing wrong with the theory of quantum electrodynamics. It is therefore, I would say, the jewel of physics, our proudest possession. Great possession, but it turns out he says he's not going to be able to explain it. He doesn't really know that, okay? Okay, he continues here. He says, will you understand what I'm going to tell you? You think I'm going to explain it to you so you can understand it? No, you're not going to be able to understand it. You see, my physics students don't understand it either. That is because I don't understand it. Nobody does. While I am describing, what? Explaining? No, describing to you how nature works, you won't understand why. In other words, the mechanism, nature works that way. But you see, nobody understands that. I can't explain why nature behaves in this peculiar way. And the reason he cannot explain it, he cannot explain it with particles. That's the problem. Okay, keep that in mind. He cannot explain it what? With particles. Okay, it doesn't mean nature doesn't have a mechanism. It means that you cannot explain that mechanism with particles. Okay, that's what I'm going to argue here. The theory of quantum electrodynamics describes nature as absurd from a point of view of common sense. No, from a point of view of particles. That's where the problem is. If you try to do it with particles, it's what he says there at the end. It's absurd. Okay? It agrees fully with the experiment, but the explanation is absurd because he's going to try to simulate it with particles, discrete particles. That's where the problem is. Okay, so he continues here and he says Newton thought that light was made up of particles. He called them corpuscles, and he was right. Oh my God, here we have religion now. Mr. Feynman's not going to allow me to present an alternative to that. He says he was right and you're wrong, Bill. We're done. Okay, this is how it works in so-called science, in so-called mathematical physics. What they do is they say it's particles all the way and you have no say in it. You can't give an alternative version of this, even today, okay? We know, I like that word, we know, they know everything. That light is made of particles because we can take a very sensitive instrument that makes clicks when light shines on it. And if the light gets dimmer, the clicks remain just as loud. There are just fewer of them. Thus, light is something like raindrops. Each little lump of light is called a photon. Okay? I want to emphasize that light comes in this form, particles. You were probably told something about light behaving like waves. I'm telling you the way it does behave, like particles. Light is made of particles. I hope you understood that, okay? What is Mr. Feynman going to talk about? He's going to talk about particles. He's not going to talk about waves. Okay? He doesn't like waves. He's going to say light is particles. But with particles, he says, yeah, it gives us absurd explanation. No kidding. I wonder why. Well, we'll find out. Okay? Hold your horses. Here it goes. You might wonder how it is possible to detect a single photon. One instrument that can do this is the photomultiplier. By the way, I used a photomultiplier at AMD, so at least I'm very familiar with it. And I discussed that in the past, and all I can tell you is the following. Photomultiplier is designed to detect any blip, any thump as a particle. And maybe that's where the problem is, because it's designed that way to count bumps or blips or whatever, and immediately converts that to a particle, and that's the so-called photon. Okay, that's what I want you to keep in mind. When a photon hits the metal plate, okay, so we're done. We know it's a photon, it's a particle. Now he's going to talk about hitting. Okay, he thinks something is traveling. That's a photon. A discrete photon is going to hit. Okay, the metal plate A at the bottom, it causes an electron to break loose from one of the atoms in the plate. And again, he's making a second assumption, which is the electron is another particle which the photon hits. You wonder how that is possible. First, because the photon is zero-dimensional, so is the electron. They have no size. And here the photon has such great aim that it's going to hit an electron that's rolling around in different places around the energy level or orbital, and it's going to hit it. Man, that's quite an important photon that it can hit an electron. First, they're both zero-dimensional. Then it's got tremendous aim because it's going to hit that electron. Okay? To break loose from one of the atoms in the plate, the free electron knocks loose even more electrons. So we have now a cascade. Okay, a chain reaction, the electron knocks more electrons. This process is repeated 10 or 12 times until billions of electrons, what is he talking about, current? A sizable electric current hit the last plate. Each time a photon of a given color hits the photomultiplier, a click of uniform loudness is heard. Okay, so that's, again, because the photomultiplier has been designed to detect any thump as a particle. It's already done. And so they say, see, light is full of is made of particles because the photomultiplier is detecting them. No. It's that the photomultiplier was designed to consider every little signal, every little thump or whatever, as a particle. That's the problem. Okay, so let's see how he explains reflection. Again, Mr. Feynman now is going to work his way to explaining the mechanism. When a photon comes down, it interacts with electrons throughout the glass, not just on the surface. The photon and electron do some kind of dance, the net result of which is the same as if the photon hit only the surface. 96% of the surface of the glass is holes that let the light through, while the other 4% of the surface is covered by small spots of reflective material. An average of 4% of the photons hitting a single surface of glass is reflected. With a second surface, the results are strange. Instead of the expected reflection of 8%, 4 from one surface, 4 from another, by the two surfaces, the partial reflection can be amplified as high as 16% or turned off, depending on the thickness of the glass. Okay, so what is he saying? We've got two surfaces. If you look at just one surface and you look at the holes and these regions, he says 96% of them is holes and just goes through, but there's 4% that bounce back from the surface. Now you have a second surface, for that glass, and now you would expect to have twice the 4%. You would have 4% at the top, 4% at the bottom. When they do the experiment, usually 16%, it goes down to 0 depending on the thickness of the glass. So now that's what they got to explain. And so the first attempt is to explain it with waves, transverse waves. James Maxwell, he came up with equation for waves. Mr. Augustin Fresnel had already proposed the transverse wave, earlier. This strange phenomenon of partial reflection by two surfaces can be explained for intense light by a theory of waves. This is what he's saying, okay? He's telling you they can explain it with waves, but the wave theory cannot explain how the detector makes equally loud clicks as the light gets dimmer. And he's got this little footnote there. He says this idea made use of the fact that waves can combine and cancel out. And the calculations based on this model match the results of Newton's experiments, as well as those done by hundreds of years afterwards. But when instruments were developed that were sensitive enough to detect a single photon, the wave theory predicted that the clicks of the photomultiplier would get softer and softer, whereas they stayed at full strength. They just occurred less and less often. No reasonable model could explain this fact. Okay, you see what the problem is? They say the wave can explain the mechanism, but the wave cannot explain the clicks of the photomultiplier. That's essentially his argument. And that's because there is no such physical object as a wave. But with a rope, we're talking about each link. That's a photon there. That's a photon. And the last link, the one that's connected to the atom right there, okay, it's constantly torquing as the atom expands and contracts and eats into that link and then releases. Eats, releases, eats, releases. Okay, and that's the thump that they count as a particle when it's really a rope extending from atom to atom. That's what we're proposing in exchange. So now we don't have the wave problem of little blips there. We can detect them with a photomultiplier, except that we got to make a change and not use the wave. Now we're going to use a rope, a physical object. A wave is not a physical object. There's no such physical object called a wave in science, let alone in physics. Okay, so what does Mr. Feynman conclude? He says quantum electrodynamics resolves this wave-particle duality by saying that light is made of particles. He solved it, okay? But the price of this great advancement of science is a what? A retreat by physics to the position of being able to calculate only the probability that a photon will hit a detector without offering what? A good model of how it actually happens. As Mr. Feynman explained, reflection. Now he says, like he started out, he ended up with how he started. He says, we can't explain it, but we're going to do it with particles no matter what because light is particles. We're done. And anyone who wants to get the microphone has to work with particles. He can't work with a rope. Okay? So he's already denying me the ability or the opportunity to speak. He's already censored me. He's saying it's particles and we're going to continue with particles. We can't explain anything with particles, but we're going to say that light is particles. That's what they're saying. Okay? Okay. How does he end his presentation? This is interesting. He says, the situation today is we haven't got a good model to explain partial reflection by two surfaces. We just calculate the probability that a particular photomultiplier will be hit by a photon reflected from a sheet of glass. Great. He's going to describe. You will have to brace yourselves for this, not because it is difficult to understand, but because it is absolutely ridiculous. All we do is draw little arrows on a piece of paper. That's all. Well, I like the fact that at least he was honest and told it like it was. You know, they have no clue whatsoever. That's the point. So don't ask them questions that they can't answer. Ask them questions that they can. That's what they're saying. And mathematical physics cannot answer explanations. They cannot answer physical interpretations, not because they're nonsensical or uncommonsensical. It's because they use it particles. That's the problem. Okay. Okay, and here we have, because you might say, well, Feynman said that in 1960s. We surely made some progress since then, right? Okay, let's find out. Here we have Mr. Matt O'Dowd, okay, and he works for PBS. I call him BS, okay? And he's going to try to resolve the issue between the Copenhagen interpretation of quantum mechanics, the many worlds, and the Bohm wave, and so on. He says, we're now approaching 100 years since the discovery of quantum mechanics. And we still don't know which of those three, you know, the Copenhagen or the many worlds, etc., versions of quantum mechanics, and we still don't know which of these, if any, are right. Okay, so what's the holdup? Okay, what is the holdup? A clue to the problem lies in the word interpretation. Okay, and interpretation of quantum mechanics is exactly that. It's a story about what really happened, what's really happening behind the math. What physical mechanism give rise to the equations of quantum mechanics? Yeah, that's what we want to know. But Mr. Feynman already finished telling us that they don't know that stuff. And here Mr. O'Dowd says, and the fact is that every prominent interpretation of quantum mechanics is perfectly consistent with the equation that lies at the heart of the theory. What do you mean it's consistent? You mean you can describe it, not that you can explain it. And he says that's the Schrodinger equation. Well, an equation can only describe it. We're not talking about an explanation. So this guy doesn't. He went off on on a tangent to left field because we're asking for an explanation. He says that what is an explanation or a physical interpretation, and he says he wants to know the physical mechanism, and then he talks about a description, and he says the Schrodinger equation what describes how the wave function of a quantum system changes over space and time, and so it should completely determine the measurements we can make of that quantum system. He's not talking about a theory. A theory is an explanation. A theory is not a description, which is what Mr. O'Dowd is referring to. So again, to this day, they don't have an explanation. And what you see out there, usually something like this, you'll see it done with particles. Okay, there you see light, a little photon hitting the surface of glass or whatever surface it's hitting, and they say that's what reflection is. The particle just hits, bounces off. That's their explanation. Okay, and so what's the problem with this? Well, there's too many problems to consider, but let me look at one by Mr. Don Lincoln, and he's a guy who works for Fermilab. He does some of these same shows. He does it for Fermilab, trying to explain what the quantum mechanics don't know, okay, because again, they don't know, they're going to describe, and this is what he says. This is out of his presentation, and you get this light coming to an interface between, for example, in this case, air and glass, and you have a reflection coming back up. But in order to explain this, he's going to use these positive and negatives there to the right, which are supposedly the atoms. Okay, so they're going to be rearranged there. You'll see that in a second. Okay, and you can see that the negatives and positives, arrange themselves in such a way that allows a reflection. What's the problem with this? Well, the problem is those positive and negatives. There is no such thing as positive and negative in physics. There's only positive and negative in mathematics. What does positive and negative mean in physical terms? And we go back to, where we are with the atom. What does an atom look like? And this is their atom. This is their positive and negative. The negative is the blue ball there going around. The positive is that black one in the center that's got the quarks being held together by so-called gluons. They throw gluons at each other, but they're held together. Who knows what that means? And they always paint them with bed springs, held together. I don't know what a bed spring looks like because I've never seen it in the standard model. Okay, and what is current? Because he's going to talk about electromagnetism, which involves the atom, and the atom, according to them, is a little ball. Again, it goes around the atom. There you see the little red balls in this case going from one atom to another, and this flow is what's called electricity. And again, all they have to answer, they have to illustrate is their atom. And if Mr. Lincoln cannot illustrate his atom, he doesn't have a case. He doesn't have a physical interpretation. Okay, that's what I'm saying. He's going to use positive and negatives. He's talking about descriptions, again, mathematical descriptions, not physical interpretations. So his so-called explanation is bunk. Bunk not because, in other words, it's not the explanation we're criticizing. It's his assumptions. He doesn't have an atom. He doesn't have a photon. He doesn't have an electron. That's the problem. Until he can settle that, and show us what his atom looks like, he doesn't have a case. He can't even start to talk. We have to remove the microphone from his mouth, and he's got to go back to the drawing board, erase it completely, and start brainstorming again. Okay, what's the rope version of reflection? Very straightforward. Kindergartner can understand it. Okay, there you see it. You have rope connected from atom to atom. So there's a rope coming from one atom. We're just looking at one rope, one atom, and we're talking about something so small, so thin. Okay, and so you got to ponder that. Here you're looking at something that Atom Man would be looking at, and the rope is very thick there. It's much thinner than that. Okay, so keep all this in mind. But the point is that light travels back and forth along the rope because it torques and it stimulates both atoms, the ones that are at either end of that rope. If the glass is thick or has different material in it so that it's not completely pure, or it's a crystal so that its crystal structure is organized in some meaningful way, then you might have differences in the wavelength throughout the glass. Okay, so you might have that situation there. And again, that's got to do with a rope, the fact that frequency is inversely proportional to wavelength. Okay, the more you have of one, the less you have of the other under the rope model. And it's very simple to understand. You know, you have the rope, the more you torque it, okay, for the same amount of rope, you have more links, and each link is shorter. That's what frequency and wavelength, the inverse proportion of frequency and wavelength indicate. And, you know, light travels at 300,000 kilometers per second. It's a constant, so little c is a constant, and it's equal to the inverse relation between frequency and wavelength. In our case, number of links times link length. Very straightforward. A baby can understand it. Okay? We're not talking about, something beyond your capability. Okay, and here you see what happens with a prism, and when you do it with waves, you can't explain it. What can we explain with a transverse wave? Well, when it goes through a prism, you know that when the light comes out, like if you put white light coming in and what comes out is colored light, as Mr. Newton showed, well, you know that those different wavelengths that come out with different colors, they have different lengths. In other words, they have different wavelengths, okay? And how do you get that from a prism? If the prism squashes, for example, right, squashes the wave so that you have either smaller or bigger waves going through there, how does that wave later on get bigger or smaller when it goes back out to air, for example? See, this is what you got to explain with the wave nature of light. Assuming you could explain the wave, you can see that the wave is what? A bunch of vectors. So what you're staring at there is something very scary. You're having mathematical vectors which are moving. They're not only moving up and down, but they're moving sideways. Very scary stuff. Okay? Under the rope model, we can explain that very easily. Here you see the rope model. Okay, we have white light coming in. Again, it's different frequencies and different wavelengths. You put them all together, you get white light. What happens when you get inside the prism? You have atoms which are connected to different atoms on the other edge. And the one that gives you red has longer lengths. And the one that gives you blue or violet, you know, on the bottom, is shorter lengths. Very simple. And why? Because those are connected to another atom that's outside the picture. Okay, that's the issue. And again, we're only showing one atom here. Really, in reality, you're talking about gazillions of atoms. Okay, but there you can see why we have colors coming out of a prism. And again, for reflection, very simple, because light travels both torsion. The torsion travels in both directions between two atoms. So both atoms receive the signal simultaneously and permanently and constantly. Okay, so it's no mystery. Okay, it's really no mystery. At least you can understand it. Whether you believe it or not, that's a separate issue. That's your personal opinion. What we're talking about here is being able to visualize a mechanism. And everybody should be able to visualize a rope torquing and sending signals, these bumps, to both atoms which are expanding and contracting and torquing the rope. Okay, so this is essentially what we're proposing. What should we conclude? Okay, let's go with the conclusions to wrap it up. Okay, here it is. Conclusions. Quantum mathematicians confess that they have no rational explanations or physical interpretations for reflection. Okay, Mr. Feynman was clear about that. The other two, Mr. O'Dowd, Mr. Lincoln, they do hocus pocus. They cannot explain it. They immediately move into descriptions, not into explanations, because they cannot explain it, especially with discrete particles. Okay? And again, you can see that they bring in the wave when Mr. Feynman says there is no such thing as a wave. Light is particles. Okay, he tells you that, but these guys say, well, let's bring in the wave so that we have this duality and we can sneak around, you know, the particle, because the particle, with that, they cannot explain it. This is due in part because quantum mechanics doesn't have a physical model of the atom, specifically the electron, or of a photon. You simply cannot explain perfectly straight rectilinear behavior, right? Whichever of the two extends straight, moves rectilinearly, okay, of light, in other words, reflection, with discrete particles. That's the big problem. Okay? Under the rope model, proposes that light propagates bidirectionally along a DNA-like rope that connects two atoms which are pumping back and forth, doing their quantum jump, torquing the rope. So it's a self-stimulating system. The atoms go back and forth, expand, eat the first link, then release it, and that stimulates the other atom, which is doing the same thing to the rope in the opposite direction. So both atoms are receiving this thump, this photon, that the photomultiplier counts as a particle. Okay, that's what's happening. And so with the rope, we don't have the same problem that Mr. Feynman showed, that you won't get the blips on the photomultiplier. Yes, you will, because again, we're talking about that little piece of rope that is thumping the atom constantly. That's the thump that the photomultiplier is detecting. The model illustrates reflection. Okay? Do you believe it? Well, that's a separate issue. Belief, we don't deal with that in science. We just explain objectively so that you understand. Whether you believe or not is your personal opinion.